So today we're going to move on to the second unit of AP Chemistry, which is molecular and ionic compounds, structures, and properties. This one is basically going to be over ionic versus covalent bonding, VSEPR, inter and intramolecular forces. So today's quote, it's the little details that are vital, little things make big things happen, by the coach John Wooden. Wooden was actually the coach of the UCLA basketball team during the 60s and 70s that won like an unprecedented number of national championships. So let's look at an item that's in ionic bond. So if you look at this, this is a particle diagram of NaCl. And we talked about this in the last unit, how Cl, when it becomes an anion, is going to be larger than the sodium, that's a cation, and you'll get basically it'll be interspersed within this lattice structure. So when you look at a salt, a little portion of salt, there's actually millions upon millions of Na and Cl ions that are then going to be formed into that structure. As you know, if you take table salt and you throw it into water, it's going to dissolve. And we call that dissociation in water. What's going to happen is that the water molecules will actually form these slight polarities around the atoms. And so the Cl that's negative, the water molecule is going to orientate to the more positive hydrogen around the negative Cl. And then the oxygen is going to orientate, the negative oxygen is going to orientate to the positive sodium on this side to make that work. It's important to know ion charge and attraction. So attraction will increase as it's smaller, and it'll also increase as you move across. So +1, -1, if they're smaller ions, will be able to form a stronger attraction than a +1, -1 that's larger. And again, that's based upon coulombic attractions between the two ions. And then if you have a +2, -2, that also will be a stronger charge than a +1, -1 if the sizes are relatively the same. And the thing to remember, greater the charge is going to be greater the bond. And so thus it's going to take more energy to break those bonds. And so items that have these greater bonds are going to have a higher melting point. So magnesium oxide, which is +2, -2, has a much higher melting point than NaCl, that is +1, -1. Over here you see the charges. If charges are the same, it's going to be a smaller ion. So you can see that LiF, again being smaller, will actually have a higher melting point because the positive cation and negative anion can get closer together than KBr. Metallic bonds, there's always, this comes up every couple of years, and it's important to recognize the difference. But when it comes to metallic alloys, there's two types. There's interstitial, which you have different size radii. So steel would be an example of this, where you have smaller atoms of carbon that are going to be intermixed within and between the larger iron. And then you have substitutional, which is similar size radii, which is like brass, where zinc and copper are relatively the same size, and so they're just interdispersed within each other. So you can kind of see with substitutional, all of them are roughly the same size. And then what happens is you just have some that are intermixed here. Where interstitial, you're going to have smaller atoms that are going to be mixed in between the larger atoms for that. So now we're going to talk about Lewis dot, VSEPR, and bonding. I'll actually cover this in class this little bit because I think it's good to demonstrate this on the board. So this part I'm going to go through a little bit quicker, and then we'll cover this one in class. So number one, when it comes to covalent practice, you always want to make sure to have your number of valence electrons accounted for. It's important to recognize what your central atom is. It's important to do single bonds first, and then double or triple if needed, and then you always check the valence electrons. So most of you have had Vesper before. We'll just review it. It's not too much more on the AP side than it was, at least for those of you that have me in honors. And it's not that much more than those of you that are coming up from regular chemistry. This year, I'm going to do examples of these in class. So I'm going to go ahead and skip the slide for now, and we'll cover it then. So Vesper actually stands for Valence Shell Electron Pair Repulsion Model, and it's the actual model shape, and it's based on the number of atoms that are attached. And atoms that are attached or atoms are lone pairs. And again, I'll give you guys the Vesper diagram. We'll go through Vesper as a class and kind of cover that. That'll basically come up shortly in the course. When it comes to Vesper, you want to do these four things. You need to count the Vesper electrons, draw the appropriate Lewis structure, determine the steric number, and then from that, determine what the Vesper shape is. I will provide the Vesper handout to you guys and go through it. So I'm going to skip this slide for now. Hybridization, it's mixing orbitals into new hybrid models. And all you need to know is you have different energies and shapes than the original orbitals, and it's suitable for electron pairing to form chemical bonds. Every year, every other year, this hybridization chart comes up. And so it's going to be really crucial for you to know what the hybridization is. So anything in steric 1 will have S and have a bond angle 180. Anything in steric 2 will be SP. 3 will be SP2, 4 will be SP3. Steric 5 and steric 6 do have their own hybridization numbers, but those never have been tested, and so we don't need to worry about them. But I would memorize this chart because whether on a free response or multiple choice, you'll maybe have to draw a Lewis structure, and then it'll ask you to identify the hybridization. If there's 4 things attached to the central atom, it's going to be SP3. And then they could ask for the hybridization and the bond angle, and these are the bond angles you guys want to know. We'll spend a little bit of time on formal charge. So formal charge kind of gets at what the overall charge is on the item and what you want. So there are structures that are more advantageous than others because you have a less charge overall. And then usually the structure that is considered the better structure is the one with the least number of ions that are associated with this. So for instance, sulfur in this orientation, sulfur is triple bonded to carbon, and then carbon is single bonded to nitrogen. Sulfur is going to be a +1 over here because we have 6 electrons. There are 2 lone pairs and 3 that are bonded, so it's 6 minus 5 to get +1. Carbon has 4 bonds to share. 0 of them are lone pairs and 4 of them are bonded, so carbon's going to be 0. Nitrogen has 5 electrons to start. 6 of them are lone pairs, and then it has 1 that it's sharing, so its overall charge is a -2. So the overall charge on this molecule would be -1. The other form on SCN is this one here, where everything is double bonded. You can see that sulfur starts off with 6. We have 4 lone pairs, 2 bonds, so it's 0. Carbon is also 0, and then nitrogen is going to be a -1. So the overall charge on both structures is -1, but this one is usually considered the slightly more advantageous structure, given there's 0 charge on the sulfur, 0 charge on the carbon, and just a -1 on the nitrogen. Let's move on to intra and intermolecular forces, which are crucial. First step is to always determine what we're talking about when it comes to this. So intramolecular bonding is bonds within a molecule. So an actual single, double, or triple bond that occurs within an actual molecule. Intermolecular forces are interactions between molecules, hydrogen bonding, dipole-dipole, London dispersion forces. So this diagram here shows you those differences. So you can see this is going to be the intramolecular bond between H and chlorine. And then this one here has an intramolecular bond between this hydrogen and this chlorine. And then the intermolecular force is this weak attraction that's not an actual bond, it's a weak attraction between these two hydrogen chloride molecules. Another example to show this is with oxygen. So oxygen is always diatomic, it's double bonded together, and so you can see the double bond between these. This is a very strong covalent intramolecular force. This is the weak intermolecular force for that to work and operate. So intramolecular bonds, I'll just go through this real quick. If you have one bond, you're going to have one sigma. It's going to be the longest, least amount of energy. If you have a double bond, you'll have one sigma and one pi. The length is intermediate, and so is the bond energy. And then for a triple bond, it's going to be one sigma and 2 pi, shortest and greatest. And every couple years they'll ask, they'll give you a structure, you'll have to draw a structure, and it'll ask you, hey, how many sigma bonds does this have? How many pi bonds does it have? So on and so forth. All you need to know is that single bonds always are one sigma, double bonds always have one sigma and the other one's a pi. Triple bonds will have one sigma and then 2 pi for that. So when looking at a sigma bond, you don't need to know what this looks like. I'm just showing this to you. But for some students, it's a little more visual to see this. So this is a illustration of what a sigma bond looks like, an illustration of what a pi bond looks like. And you can see this would be the sigma bond here between this carbon and this carbon. And then this would be the sigma bonds here between the carbons and hydrogens. And then when we deal with pi bonds, this one here, you can see we have a sigma bond here between these carbons. And then there's a pi bond, and the pi bond basically encapsulates or circles it. So this is part of the pi, and this is the other part of the pi that's around it. And then in a triple bond, you're going to have the sigma bond is the yellow. One of the pi bonds is the blue, and the other pi bond is the purple. So I'm just showing you the orientation, but you won't have to draw that. All you have to know is that single is one sigma, double is one sigma, 1 pi, triple is one sigma and 2 pi. Network covalent structures. We talked to this a little bit at the beginning when we talked about NaCl. You're going to have this lattice of covalent bonds, and there's one gigantic structure that's there. So that's it for the notes over this unit. As you can see, there's a lot of little things that we'll need you in class when it comes to Lewis dot and Vesper and whatnot, and just separating inter from intra-molecular forces. But we will cover all this. So if you have any questions, say those to class or let me know. And we will talk about this later.